Okay. So one thing one announcement I want to make sure is on record, now that we're recording, is now we're going to have 7 homeworks altogether, but the lowest homework grade will get dropped, so only 6 of the assignments absolutely need to be turned in. And the last one for chapter 7, I'm not sure how far we'll get into chapter 8. It depends on how quickly we move through things, but so the last homework assignment will actually be covering chapter 7, and I just realized that I have printed out my notes for this lecture, but they're still in my office, so I need to quickly grab those and then we can get in.
Yeah, you get, yes, you get 1 half for 1, and you get 1 fourth for 1.
Okay.
Here?
The main with this looks like that. And that
Okay. But again, I imagine several of you will be focusing on finishing up your analysis midterms anyway. So, okay.
Spectral-related, which it cannot be the case, right? You need a posting for it.
All right, so we're continuing with section 6.4, so properties of Sturm-Liouville eigenvalues and eigenfunctions. Okay, so several properties that were established last time is that the eigenvalues and it's possible to make the eigenfunctions real. I mean, eigenfunctions can be really complex because you can multiply them by anything, but the point is it's possible to obtain real eigenfunctions. And the eigenfunctions are also orthogonal. So it's possible to get an orthonormal basis of eigenfunctions. Okay. Also, well, really the first property that we proved that was used to prove the other ones is that the Sturm-Liouville operator is self-adjoint or symmetric. Okay. Meaning that ULV that this condition is satisfied. Okay.
Is that that's a bracket, right?
Um,
An open bracket to the left. The very front. It looks like a squiggly.
oh, here?
Yeah.
That's meant to be a square bracket.
Okay.
Yeah. But yeah, that did look kind of squiggly. All right. Now, for the next property, okay. So, the eigenvalues of a regular Sturm-Liouville problem are simple. And all right. And by that I mean they have multiplicity 1. So there's only one linearly independent eigenfunction that these eigenvalues have. Now, before I prove this, I want to refresh memory. By regular, that means I'm not talking about the periodic Sturm-Liouville problem. So a lot of these properties, like these other ones here that were established last time, they do apply to both a regular and periodic Sturm-Liouville problems, but this one only applies to regular, because for periodic, you can have eigenvalues that have multiplicity 2. You can have sine and cosine both being eigenfunctions. And refresh your memory, after all, it was 5 days ago. So what I mean by a regular Sturm-Liouville problem, you have same ODE in both cases, this same eigenvalue problem, but where the difference is in the boundary conditions. So you have alpha u of v plus beta, sorry, not u of v, u of v of a, beta v prime of a is 0, and then similar boundary condition at x equals b. Okay, so these are regular, so these are boundary conditions that are regular Sturm-Liouville problem has. So when you have this ODE, and these boundary conditions, the eigenvalues are going to be simple. Okay, so now I'll take some time to go ahead and prove that, and let's see if I can switch the computer from one board to the other without having the recording stop like it seemed to want to do last time. Okay, so keep a close eye on it. Okay, still recording. Okay, so to prove this, all right. Let's assume that we have two eigenfunctions, v1 and v2, with the, oh, I just realized on the previous board, slight mistake, there's no minus here. And that's because there is supposed to be a minus in this whole equation, but I've already included it up here, so I did not need it down there. Okay. All right, so fix that in your notes. Okay. So now I have LV1 is lambda r v1, and then I have a second eigenfunction v2, lambda r v2. So in other words, v1 and v2 are eigenfunctions with the same eigenvalue, lambda. So the idea is, I want to prove that v1 and v2 cannot be linearly independent, because if they were, then lambda could not be a simple eigenvalue. Okay. So let's see what happens. Because if I look at v1 LV2 minus v2 LV1, there are two different ways to approach it. So first, not yet looking at, not yet taking into account the assumption that v1 and v2 are eigenfunctions, but for functions v1 and v2 in general, we have v1, and then LV2 is defined on the previous board, so I'll take that into account. So I have minus P1 V2 prime prime plus Q V2, and then I have minus V2 LV1, but LV1 is minus, making this a plus, PV1 prime prime plus QV1. Okay, so now I want to simplify this. Well, the Q terms are going to cancel because I have minus QV1 V2, and over here I have plus QV1 V2. So the Q terms are gone. Okay. Now the next thing I'm going to do is expand these derivatives using the product rule. So I have minus V1 P1 V2 double prime minus V1 P1 prime V2 prime. And then similar for the other term, so I have plus V2 P V1 double prime plus V2 P prime V1 prime. Okay. So now I'm going to group these together. Wait. There's no subscript with P. It's just P by itself. Okay. So I'm going to group the P terms together. So I'm going to have P, and I have V2 V1 double prime minus V1 V2 double prime. And then I'm going to group the P prime terms together. And that's going to give me V2 V1 prime minus V1 V2 prime. Okay. Now, so the next thing I'm going to do is, in this expression here, I'm going to add and subtract V2 prime V1 prime so I add it here and I'll subtract it off here. Okay. And I still have this other stuff. Okay. Now, it turns out that if you were to take this expression over here and differentiate it, well, you need the product rule. So what would I get differentiating this by the product rule? V2 V1 double prime plus V2 prime V1 prime. In other words, exactly this. So this is V2 V1 prime prime. This over here, I have, if I were to differentiate this, I'd have minus V1 prime V2 prime minus V1 V2 double prime. So this is V1 V2 prime prime. Now actually, so I can condense this. This is P V2 V1 prime minus V1 V2 prime prime plus P prime V2 V1 prime minus V1 V2 prime. Okay, now, how can I condense this even further?
How did you get that prime?
Get what?
That prime?
This one?
Yes.
Yeah, because,
That product rule in there.
yes. Now, because since all of this turned out to be the derivative of what's in here, so this, basically, it's product rule in reverse. So this is this whole expression.
Oh, okay.
Yeah.
I was writing down the wrong thing.
So now how can I condense this?
It's just P and all that prime.
Yeah, so it's P times V2 V1 prime minus V1 V2 prime, all prime. what that means is, if I define function q of x to be equal to p of x times all that, so v2 of x, v1 prime of x, minus v1 of x, v2 prime of x. Alright, so it's just that without that final derivative. So in other words, I'm defining q, capital Q, to be whatever is inside the differentiation. Okay. Actually, I can't tell you anything about that just yet because I have a little bit more to work out, but hold on to this.
You mean v2 prime of x in the last?
Yes, v2 prime. Okay. Now, actually, off to the side here, work out an alternative expression for this. Where now I'm going to take into account the fact that v1 and v2 are actually eigenfunctions. Well, LV2 is lambda RV2, and then LV1 is lambda RV1. But how does... Oh, I should mention, okay, the notes, I forgot the R. It turns out not to really affect anything. But how does that simplify? Yeah, 0. Okay. So in other words, so this whole thing here is 0. So, in other words, q prime is 0. So what does it say about the q of x itself?
Constant.
Yeah, q of x is a constant function. Okay. Now, here, though, we use the fact that, so we have not yet used the fact that v1 and v2 are eigenfunctions of a regular Sturm-Liouville problem. But now we are about to use that. And actually, I'd rather not change boards, so I'm going to squeeze in the rest of this up here. So, because it's a regular Sturm-Liouville problem, that means that and this is something we came across in proving the self-adjoint property before. It turns out that q of A and q of B are 0. And this stems from the fact that v1, v2 satisfy the boundary conditions. So we've not yet used those until now. Okay. Like you can see this most easily in certain special cases, like the Dirichlet case. So v1 and v2 both equaling 0 at both boundary points. That would definitely make this expression 0. So not only is q of x a constant function, we now also know that that constant is 0. Okay. But p of x, this coefficient here, is not 0. In fact, for a regular Sturm-Liouville problem, I can say something more. It's positive. So that's one of the conditions about being a regular Sturm-Liouville problem. It's not just the boundary conditions. There are certain assumptions on the coefficients that were stated way back when I first started covering this chapter. One of them is that p of x is a positive coefficient. Okay, so if that's positive, then this whole expression down here, 0. So let me repeat that up here. So v2 v1 prime minus v1 v2 prime is 0. Now this expression, whoops, that 2 belongs down here, v2 prime. It's been that kind of a day. Now, this expression, v2 prime, v1 prime minus v1, v2 prime, this expression came up a lot in your first differential equations class. What is it called? When you have two functions, and you do this thing, you take one function times the derivative of the other and then subtract it from the opposite combination. So this in general, what do we call this? From theory of ODEs, what?
Separation.
No.
No.
That's what I was thinking too. Here's just a hint.
I guess that's the biggest hint you can.
Okay, then you're gonna end up
The
getting
parameter thinking about? No. The parameter.
v2 over
never mind.
v2 prime equals v1 over v1 prime, right?
Well, I wouldn't go there because
That's not the thing.
yeah. So there's an actual name for this.
Here's the thing we
Where does
did.
it start
The
with?
sixth one.
W.
A Wronski?
Yes, it's a Wronskian.
What's up? Okay,
Yeah,
sorry.
but use the determinant for it. Don't you? Yeah, it is
yes,
the
it's a
determinant.
determinant.
That's what it is.
Okay.
Yeah.
All right.
Remember?
Yeah. So this
Yeah.
is for Wronskian v1, v2. Okay. So if a Wronskian of two functions is 0, what does it tell you about the functions?
They're linearly dependent.
They're linearly dependent. So, and these were any two eigenfunctions. So if any two eigenfunctions of the sturm-Liouville problem with eigenvalue lambda have to be linearly dependent, that means that lambda is a simple eigenvalue. So each eigenvalue of a regular Sturm-Liouville problem only has one linearly independent eigenfunction. Okay, and the thing is, if I've been looking at a periodic Sturm-Liouville problem, all of this still would have applied, but I would not have had this. So that's why this property doesn't apply in the periodic case. Okay. So any questions about all these manipulations?
In the periodic case, p of x could be 0.
Well, no. Generally, this would still be a positive coefficient, but you do not have. Let's see. Actually, in certain periodic cases, you could. Well, like if. Oh, wait a minute. Yeah, you do not have these conditions satisfied.
Right.
Yeah.
The boundary condition.
Yeah.
Right. Then we cannot say that q of x equals 0
Right.
everywhere. So that
Yeah. Okay. Keep recording. Okay. All right, so the next property. Actually, I'm not going to prove, that would be a very tall order indeed. So what we know about eigenvalues is that some of all eigenvalues of a regular Sturm-Liouville problem is a monotonically increasing sequence. So you have 0 strictly less than lambda 1, strictly less than lambda 2, and so on. And not only that, because you could have a case where you see this in real analysis, where you have a monotonically increasing sequence, but it is bounded, therefore converges to a limit. But that does not happen in this case. So the limit as n goes to infinity is infinity. So the sequence of eigenvalues is not only monotonically increasing, it is also unbounded. Okay. Now, I've emphasized here this is a regular Sturm-Liouville problem. You have similar behavior for a periodic one. So the only change I would make is that up here you can just say less than or equal to between all the eigenvalues, just because those monotonically non-decreasing, and the only reason for that is because you can have eigenvalues of multiplicity too. So if you were to look at, if you were to consider each pair of identical eigenvalues as a single entity, then from pair to pair you still have monotonically increasing, but you have to take multiplicity into account. Okay. Now, another. Okay. So one consequence of this fact that you have these countable infinity of eigenvalues is, and this applies for both regular and Sturm-Liouville problems. That is a regular or periodic Sturm-Liouville problem has an infinite sequence of orthonormal eigenfunctions. So really, I'm combining several properties into one that can be used to prove this. Okay. And also these, so these eigenfunctions belong to this space. So this is the set of all piecewise continuous functions on the interval AB. And the weight function is R. So when I say orthonormal eigenfunctions, they're orthonormal with respect to this inner product. So we have the integral in B of Vi Bj with wave function R. So you have to include that. It's equal to delta Ij. And remember, I brought this up last week. Kronecker delta, so this is equal to 1 if I equals j, and 0 otherwise. All right, so we're orthonormal with respect to this inner product with weight function R. All right. Another fact about the eigenvalues and eigenfunctions that the eigenvalues, while not being bounded above because they go to infinity, but they are bounded below. Right, and there's certain assumptions in the coefficients, like if a coefficient p is positive, for a regular sturm Liouville problem, and a coefficient q is non-positive, you can prove that the eigenvalues are all strictly positive. Or actually, no, they're non-negative. So for instance, if q of x equals 0, you could have a 0 eigenvalue. Okay.
Will they always be bounded below by 0?
Depending on the coefficients, it is possible to have a negative eigenvalue. For most problems of interest in applications, like heat equation, wave equation, and so forth, all the eigenvalues are non-negative. Yeah. Because having negative eigenvalues can correspond to physically unreasonable phenomena, like the heat equation backward in time is ill-posed, and stuff like that. Yeah. Okay. All right, let's see. Wow, it's a lot of notes covered. Okay, we're doing on time. Eesh. Okay. Oh, still recording at least. Okay, the next important property is completeness. Okay. So a set of orthonormal eigenfunctions that we have so Vn going from 0 to infinity is actually a basis for this function space, piecewise continuous functions on AB. So, in other words, this function space is complete. Another way of putting it is a Hilbert space. In other words, you can express any piecewise continuous function on AB in terms of the linear combination of the eigenfunctions of a regular or periodic sturm Liouville problem on AB. Okay. So, in other words, if I have a function v that's in this space, I can express v as a linear combination of coefficients an, vn. So an are the coefficients of this infinite linear combination, and the coefficients I can get by taking the inner product of Vn with V, and that is integral Vn times V, and don't forget the weight function R. Now, I'm going to put the complex conjugate here because that's in the definition of the inner product, although from a previous property, the eigenfunctions can be chosen to be real, so it's not necessary in that case. Okay. So this is called an eigenfunction expansion. Very useful tool for representing solutions of PDEs. Because what you do is, for these time-dependent problems that can be separated using separation of variables into a sturm Liouville problem and then a time-dependent ODE, you solve a sturm Liouville problem, you get the eigenvalues and eigenfunctions, you solve a time-dependent ODE, and then you can assemble your solution from that as an eigenfunction expansion. And to get the coefficients, you fall back on the initial conditions. and the solution to your time-dependent ODE. And we're going to use this on Wednesday when we get to non-homogeneous PDE that we can solve using these eigenfunction expansions. Okay. Now, here's some properties of this eigenfunction expansion for a regular or periodic Sturm-Liouville problem. And that is, there's two parts to this. If f is continuous and at least piecewise differentiable, so in other words, the graph is allowed to have kinks in it, or corners, like an absolute value of x. So that is an example of a function that is piecewise differentiable because the derivative is -1 for negative x and +1 for positive x. It's not differentiable at 0. And if it satisfies the boundary conditions of your Sturm-Liouville problem, just like the eigenfunctions do, then your eigenfunction expansion of f converges uniformly to f on the interval AB. Now, the quickest way I can describe what I mean by uniform, being uniformly convergent, as opposed to just plain convergent. Like, there's two notions of convergence here. There's point-wise convergence. In other words, at each individual x, your expansion converges to f of x. And a stronger notion of convergence that's uniformly convergent. So, point-wise convergence, you're saying that the limit as n goes to infinity of, actually I use capital N, of this partial sum at each individual x is f of x. So in other words, so for each x in your interval, you have an entirely separate limit that exists. And you've all seen from analysis, definition of limit, delta epsilon. So for all epsilon greater than 0 there exists, we're talking about a sequence here, so some value n naught, such that if n, capital N is greater than or equal to n naught, then this difference is less than epsilon. But I'm going to specify that my n naught here in my definition of limit actually depends on x. So I'm going to call it n naught of x. In other words, convergence might be faster at some values of x than at others. So this is what I mean by point-wise convergence. Uniform convergence. So now that I've laid this out, it's actually very easy for me to describe a distinction between point-wise, weaker point-wise convergence and stronger uniform convergence. And that is n naught is independent of x. So you can find one value of n naught that applies to the entire interval AB. Because whereas in point-wise convergence, if uniform convergence is not possible, it's possible that n naught could be arbitrarily large. So you may have extreme difficulty, very slow convergence at certain points. Okay. But what this proposition says is, if you have a well-behaved function, so continuous, differentiable except maybe certain isolated kinks, and it satisfies the boundary conditions, that's very important. So if you have all those things, not only does it converges quite well, converges pretty rapidly, and that's important because that means you can cut off this expansion, like if you're working with this numerically, you can cut this off after relatively few terms and have a decent approximation. Okay. All right, so that's one half of the proposition. I still have the other half, where I discuss what happens if you don't have these conditions, these nice conditions satisfied. What if f is not so well behaved? So the other half of this is if f is piecewise differentiable, and sorry, I feel like I'm moving here. On this interval, then the eigenfunction expansion of f converges to the average of the left-hand limits and the right-hand limit. Sorry, the left-hand limit x minus and the right-hand limit x plus. So this is a limit as y approaches x from the left, and this is similar, approaching, f of y, and this is approaching from the right. So in other words, if you have a function that is, because notice I didn't say anything about continuous. F is allowed to be discontinuous. So if you have a function approaching these different left-hand and right-hand limits, so this is f of x minus, and this is f of x plus, then this value in between the eigenfunction expansion converges to that average of them. Okay. So this is important for jump discontinuities in f. It's going to converge to the average of the values on either side of the jump. Okay. Okay. So now let's look at some examples of these kind of eigenfunction expansions with well-behaved or not so well-behaved functions. So, this example, let's let f of x equal 1. And we have our Sturm-Liouville problem. V double prime plus lambda v 0 between 0 and L. We have Dirichlet boundary conditions. So v is equal to 0 at the endpoints. So notice this function right here, this f of x, does not satisfy the boundary conditions. So right off the bat, you know that you're not going to get a nice uniform convergence, chances are, that we saw from the first part of a proposition. Now, this Sturm-Liouville problem has these eigenfunctions, so make them orthonormal. So Vn is equal to square root of 2 over L sine n pi x over L. And for convenience, you start indexing at 1. I've been using zero-based indexing, but it doesn't really matter. Whatever's convenient. Okay. So now what I'm going to do is I'm going to compute the okay. So I'm going to go ahead and compute the eigenfunction expansion, and we'll see how it behaves. So I have this sum from 1 to infinity of an Vn of x. And actually, the notes I have b sub n, so I'll stick with that. So this is an approximation to 1, and each coefficient is the inner product of Vn with f. So that's going to be the inner product of square root of 2 over L sine n pi x over L with 1. So that's going to be the integral from 0 to L of square root of 2 over L sine n pi x over L times 1 dx. So this integral, fortunately, is easy to work out. Integral of sine is minus cosine. So I have minus square root of 2 over L over n pi, cosine n pi x over L with limits 0 and L. Now, when I plug in the limits, so I plug in x equals L, so I can simplify this. I'm going to get minus square root of 2L over n pi. And then I get cosine of n pi. What's cosine of n pi? We've come across that before.
1 in, like, in
1, negative 1.
Yeah, it just,
just
yeah. Yes, that's what you
Same thing.
yes, that's what Corey said. I heard you say that. Yeah, 1 and negative 1.
it's not as loud as him.
Yeah, but I still heard you. So, okay. Well, I want to see if you arrived at the formula for it, the nice, concise formula. Yes.
Negative 1 to the end. Yes.
For the upper limit, and the lower limit we get cosine of 0, but that's just 1. Okay. So if n is even, this cancels out. So we get 0 if n is even, and then we get okay, if n is odd, we're going to get minus 2 here, so the minus will cancel with this minus. So we get 2 square root of 2L over n pi if n is odd. So we only have the odd number terms. So I'm going to let n equal 2k minus 1. So now k is going to go from 1 to infinity, and we'll just use 2k minus 1 throughout to account for all the odd numbers. So now I can go back and fill in my eigenfunction expansion. So I'm going to have square root of 2 over L. Well, okay. I have this, so I'm going to have a sum from 1, k equals 1 to infinity. And then I have this coefficient formula, so that's going to be 2 square root of 2L over n pi. And then I have the eigenfunction. So this is Bn, which is, oh wait, not n pi. It's going to be 2k minus 1 pi. I have to express everything in terms of k now. Okay. Then I have the eigenfunction. So that's square root of 2 over L sine 2k minus 1 pi x over L. So now I can go ahead and simplify this, because the square root of L's cancel above and below. And then I have 2 square roots of 2 that simplify. So now I'm going to get 4 over pi sum k equals 1 to infinity. And then I have 1 over 2k minus 1 sine 2k minus 1 pi x over L. Okay, so this is my completed eigenfunction expansion of f of x equals 1. Alright, so I just use n equals 2k minus 1 throughout because I only want the odd terms, the even number terms are 0. So any questions about how that was arrived at? This right here is Vn, which is V2k minus 1. Alright. Now, kind of hard to believe that this is going to be equal to 1. Although, the problem is, what I actually did was, after I got this, while preparing these notes, I actually went to MATLAB and plotted this sum, truncating it at various values. I wanted to see it get closer and closer to f of x equals 1. And what actually happens is, on the interval 0 to L, this function has to be equal to 0 at the boundary, which 1 certainly is not. So you get a behavior like this. It still goes down to the boundary, and then you have these oscillations near the boundary. And as you add enough terms, it appears to be very close to 1, except for some deviations that you can hardly see. But as you get closer to each boundary, you have these high-frequency oscillations, and then it abruptly goes down to the boundary. So these oscillations, that's Gibbs phenomenon. And that's because we do not have this uniform convergence due to not satisfying the boundary condition. And if you only have a few terms, you don't have very good agreement with 1 at all. It's very oscillatory in here. But as you add more and more terms, you get less oscillation in the interior. It starts to look like a constant function. But these oscillations, they don't go away entirely. And maybe if you had like a gazillion terms, you wouldn't be able to see them anymore, but they're still there. Because you're always going to have it jumping down to the boundary. And so what happens is, near the boundary, the series is still converging to 1. It's just taking many more terms to get there, as opposed to when you're over here. So in other words, you do not have uniform convergence. You only have pointwise convergence. Okay. So in general, we're trying to expand a function f of x in terms of eigenfunctions. The eigenfunctions satisfy certain boundary conditions. If your f of x does not satisfy those boundary conditions, you're going to get Gibbs phenomenon. So any questions on that? Okay. I'm going to do another example now. Well, actually, I made too strong a statement just now. I said, if your function does not satisfy the boundary conditions, then you're going to get Gibbs phenomenon. That's not always true. And I have to say that because, well, not because that's the truth, but also because this next example is going to illustrate that. So you're going to have some bad behavior, but it's not necessarily going to be reflected in these highly visible high-frequency oscillations. Now, here's what I can say, though. If you have Dirichlet boundary conditions, like we just did in this example, and so your eigenfunctions are all 0 at the endpoints. If a function you're expanding, your f of x, is not 0 at the endpoints, then yes, you will get Gibbs phenomenon. But where you always will, if your functions fail to satisfy boundary conditions, it depends on the boundary conditions. And that'll be illustrated in this next example.
You have Neumann conditions.
Yes. Good guess. Yeah. Well, yeah, I mean, what else are you going to have, really? I mean, yeah, there's mixed boundary conditions, but
Then you have the derivative equal to 0, which means it will be a constant.
well, yeah, horizontal tangent.
Something like
Yeah.
that, yeah.
Yeah, so you're going to see some interesting behavior, just not the same as what we had in the last example. So in this example, f of x is x. And our Sturm-Liouville problem, same PDE, but now we have Neumann, so same interval. We have Neumann boundary conditions. So derivative is equal to 0 at the endpoints. Now, this function, f of x equals x, its derivative is 1, so it definitely does not satisfy these boundary conditions. So something's going to go wrong. But once we compute the expansion, I'll draw a graph for you, and you can see what I mean. So now your eigenfunctions. So we have our orthonormal eigenfunctions. The v0 is a constant function, square root of 1 over L. And our other eigenfunctions for positive n are square root of 2 over L cosine n pi x over L. Okay. Now, so your eigenfunction expansion is going to be your constant function times a0, your first coefficient, and then you have sum of a n times your other eigenfunctions. Okay. And then to get your a's, you have inner products. So a0 is the inner product of square root of 1 over L with x. So that's square root of 1 over L, integral from 0 to L of x. Worked out easily enough. And so you get x squared over 2 from 0 to L. So when you work all that out, you have L squared and then L to the minus 1/2. So this is L to the 3/2 over 2. So that's that coefficient. Now, for the other coefficients, if an is the inner product of square root of 2 over L cosine n pi x over L with x. So square root of 2 over L integral of x cosine n pi x over L. Now, how are you going to work out this integral? What do we need to use here?
Parts.
Yes, integration by parts. So yeah, this one's a bit of a pain. Now you use your x as your u, cosine as your dv. So you're going to have x. Well, then you integrate the dv, so you're going to have L over n pi, so 1 over the constant, x sine n pi x over L with limits 0 and L. Although what's going to happen when you plug in the limits for that? What are you
It's
going to?
gonna go away.
Yeah, it's going to go to 0. So now we can focus on the rest. So we're going to have minus integral of v du. Well, du is just going to be 1. So you have sine n pi x over L. Okay, so what you're going to end up getting is, so you have 2 over square root of L. You have this L over n pi from before. You're going to have another L over n pi from integrating that. So you're going to have L over n pi squared. And you're going to have cosine n pi x over L with limit 0 and L. And that came up before. So you're going to get minus 1 to the n and then 1 when you plug in the limits. So you're going to get 0 when n is even. And then you're going to get minus 2L square root of 2L over n pi squared. Okay. Oh, I goofed here. This is not 2 over square root of L. This is square root of 2 over L. Okay. All right. So it's equal to this when n is odd. So now you can put everything together. So your eigenfunction expansion is x is equal to, so we have square root of 1 over L times L to the 3/2 over 2, but that simplifies to L over 2 for your constant term. And then you have minus, and you have square root of 2 over L times all this. And that is going to, so by the time it all simplifies, well, I'll write it out once and then condense it. So we have square root of 2 over L from here, and then you have the sum, k equals 1 to infinity, so again, odd numbers. And you're going to get 2L square root of 2L over n pi squared. That's going to be 2k minus 1 pi squared cosine 2k minus 1 pi x over L. So once you simplify that, you're going to get L over 2 minus 4L over pi squared sum of what's left here that depends on k. So 1 over 2k minus 1 squared cosine 2k minus 1 pi x over L. Okay. So how does this one behave? One thing that's interesting is, if you look at the series expansions from a previous example and this one. In the previous example, you had a factor of 1 over 2k minus 1 to the first power. Here we have 2k minus 1 squared. That's actually going to help the convergence. Because if you recall when we learned about series, like you had the harmonic series, 1 over n, that doesn't even converge at all. And whereas 1 over n squared does. So the more rapidly the coefficients decay to 0, the better behaved the expansion. So the more rapidly the expansion converges to your f of x. So you'd like to have this rapid decay rate of the coefficients. Then you can cut off the expansion at a certain point and have a decent approximation. Now, what about issues like Gibbs phenomenon and all that? Because here we have a function x that does not satisfy the boundary conditions. And what ends up happening is so what you want to get is this. This is f of x equals x. I'll zero to L. But if you were to compute this up to a certain point and graph it, and I actually did this in MATLAB, what you find is it actually approximates x very well most of the interval, and you do not see Gibbs phenomenon. But you can tell there's a little hook there that it's at the, so it's slope equals 1, 1, 1, 1, and then at the last minute, slope goes to 0. So you have this barely perceptible horizontal tangent. So technically the function still satisfies the boundary conditions. But as you compute more and more terms, that sudden turn to a 0 slope becomes less and less visible. So it's approximating f of x equals 1 on more of the interval. And in fact, what you can say is the expansion converges uniformly to x on the interval 0 to L. So Neumann boundary conditions is a slightly different story than when you have Dirichlet boundary conditions that are not being satisfied, because the function is still free to assume whatever value on the boundary that it wants. The constraint is only on the derivative. So because the eigenfunction expansion that has to have a zero derivative on the boundary does not have to make this significant jump. So there's not this abrupt discontinuity like there is in the previous example. That's why you don't get Gibbs phenomenon. So there's still anomalies at the boundary, but it's not it's not as problematic.
So as k goes to infinity, that hook thing goes away and becomes more smooth.
To the naked eye, yes.
And then you can sort of conclude that it converges uniformly because it doesn't. It's not as big a factor.
Right, yeah. And the thing is, if you were to actually try to do a delta epsilon on this,
Right.
that'd be quite a terrible exercise. But you could show that you could find a delta or an n naught that works on the whole interval.
It's less than delta.
Yeah, yeah. So in other words, you can show convergence at a similar rate across the whole interval for all x. Okay. Yeah. So failure to satisfy the boundary conditions, it is a problem no matter what, but it's not always as big a problem as in this last example here. Okay. I only have 3 minutes left. Okay. Let's see. I'm going to stop here because this is a better stopping point than anything else I can do in the next 3 minutes. So I didn't get through everything, but that's okay. We'll just pick up it on Wednesday. Okay. At least this time, we have a successful recording.